Alrighty, let's get started. So let's start off from where we were last class, and we'll build from there. So some logistics. You all should have picked up your car, or I guess today is Wednesday, right? So you should pick it up. You should have picked it up yesterday or today. Homework should be, or project one should be due on Jan 21st. End of day. If you think there'll be some delays, let me know. We'll accommodate. Again, the other logistics are the same. Any issues that anyone's having? Access, Teams, anything? No? Got your car, got your workstation? Yeah. Sweet. Let's do a little recap. Before we do the recap, let's just do our usual quiz. Question is, why do Bayesian filters need to be probabilistic? You don't know the measurement model, you don't know the motion model. The motion or measurement model may be incorrect. We can maximize entropy. Tell me how to stop. Yeah. Okay. Maybe 10 more seconds. You want to scan the thing real quick? You got it right on time. Yeah, maybe 10 more seconds. I'll just take a picture of this real quick before I keep going. Yeah, sweet. Okay, let's keep going. The answer is because your motion or measurement model may be incorrect. So you want to have uncertainty to deal with model inaccuracies or model incompleteness or things like that. Okay, so the fundamental problem we've been trying to solve is that of state estimations, right? And so the reason you need to estimate state is because state is unknown. All you observe is your previous actions and your measurements, right? So actions are U, measurements are Z. You need to estimate XT given Z1 to T, U1 to T, right? And so you're trying to build a belief, which is the probability of what the likelihood is of being in each state, given your history, Z1 to T, and your history of measurements, Z1 to T, and actions U1 to T, right? And so you often call these posteriors, etc. We talked a bunch about Bayesian filtering, but they're all trying to solve this problem. And the challenge is often representing it in a way that's tractable. So we talked about doing it with a table that can become intractable for a large enough space. And so the problem of Bayesian filtering was trying to derive a recursive update that tells you belief xt, which is P of xt given Z1 to T, U1 to T, given these three quantities, which is previous belief, your measurement model, and your dynamics model. Right? So your measurement model tells you the likelihood of a measurement being obtained given a state. The dynamics model tells you what's the likelihood of the next state given your previous state and action. Belief is something you update recursively. Starting from an initial belief, you keep updating it, right? So you may have an initial belief that you don't know where the robot is. You're going to then update it by taking measurements and then move the belief according to actions that you take, right? And so we're going to, or like what we did last time was try to connect belief xt to, these three quantities. Okay, does anyone remember how we did that? Like there was two steps we covered. What were they?
So we had prediction and then we had correction.
Yeah.
So prediction is take the uncertain estimate, the us step, and then you generate an initial I guess set of beliefs where you're just expanding the uncertainty space, and then you shrink that using the measurements that you've just got.
Yeah.
To see which one that apply.
That's right. So approximately, what we tried to do, we started with the belief at xt minus 1. We followed two steps, the prediction step, which goes from belief at xt minus 1 to belief bar at xt. Right, so remember that belief bar, let's make sure we redefine these things. Belief at xt minus 1 is P of xt minus 1 given U1 to T minus 1 and Z1 to T minus 1. Belief bar at xt is p of xt given u1 to t is z1 to t minus 1. So notice that the indexing here has changed and here has changed. And belief at xt is p of xt given u1 to t, z1 to t, right? So the change from here is the measurement. The change from here is like the quantity you're estimating, and you've incorporated one action. Okay? And so we're going to start from belief at xt minus 1. And the prediction step is going to say that your belief bar, which is just incorporating the action, is belief at xt minus 1 multiplied by the motion model, which is p of xt given ut and xt minus 1 summed up over all xt minus 1, right? So it's like to get the likelihood of a particular state, look at all previous states, look at the belief you're in that state, and the likelihood you transitioned to the state you're querying at the next time step, given you're in that previous step, given your motion model, right? So it's like, if I was here, my belief was like this. I move my action set to go to the left. My belief bar is probably going to be here to the left with slightly increased width, because there's uncertainty that comes from motion, right? Does that intuitively make sense, right? And belief correction is saying that now you've moved your belief according to action. You can also take another measurement. That additional measurement is going to shrink your belief. So you're going to go from belief bar to belief, and essentially you're going to use Bayes' rule to do it. So you're going to say, take the previous belief, multiply it by the likelihood you got that measurement at that state, and then normalize it to be a proper probability distribution. So the normalization factor is basically a 1 over p of zt xt belief summed up over all xt, right? So you want it to be a proper probability distribution. Does that make sense? So this is saying like things that were like increase the likelihood of measurements, which were increase the likelihood of states for which the measurements are likely. That's it. Okay. So we're going to work through two examples to kind of make this more clear. But I wanted to convey the intuition here. Okay. Good. Any questions? Alrighty, let's work through. So we're going to start with some examples, then we'll talk about motion models. So the examples will be abstract, they'll be tabular. Then we'll talk about how to instantiate this for your car. So we'll define what is the motion model of a car and the observation model of a car. We're almost 100% not going to get through all of this, but we'll make a strong attempt. Okay, so let's start by thinking about this example, which is you have a robot trying to open a door. Right? And so the state of the door can either be open or closed. So that is the state of your world. There's two states. There's open and this closed. And you have two actions, which is to pull the door or to leave the door. Right? And your system is going to like just transition between open and closed when you take actions pull or leave. Right? And so when you say C, it's going to be closed. When you say O, it's going to be open. Right? And so the dynamics of our system, which is going to be P of xt given xt minus 1 and ut, is going to be defined as follows. Right? So this says that if your system was already closed, right? The door was closed, and you pulled the door open, the likelihood that it is going to be open is 0.7, and the likelihood it's going to be closed is 0.3. Right? So if you were closed, you executed pull, this is the likelihood you're going to be in open at the next time step. This is the likelihood you're going to be at closed. So why is it not 1 and 0?
Or might be locked.
Door might be locked, yeah.
It could slip.
It could slip, right? So there's unmodeled effects, and we're trying to like incorporate those unmodeled effects into our uncertainty. Right? And so this is the likelihood we're gonna start when you're at close and you take pull, you get to open and closed. We can write a more complete model in terms of like a full matrix. So this full matrix is going to be, if you are closed, what is the likelihood you're open? If you're closed, what is the likelihood you're closed? And you'll have a corresponding column, which is if you're open, what is the likelihood you're open? If you're open, what is the likelihood you're closed, right? So these are the previous time step, and these are at the next time step, right? So you can kind of represent this as a matrix. So you can kind of think of the matrix as on this axis, you're going to have like previous time step. On this axis, you're going to have next time step, right? And so you can say like, on this axis, you'll have the previous time step was open and closed. On this axis, you're gonna have the previous time, or the next time step was open and closed, right? And so it tells you the likelihood of transitioning from open to open, open to closed, closed to open, and closed to closed, right? So whenever you're thinking of like, it's easier to represent them as matrices because you can use matrix multiply, etc. But it's like I'm going to leave this reference up here so you know exactly what the matrix is going to be, right? And so we'll unpack it a little more, but that just an easy way to think about it is that your x-axis here is going to be the previous step, and your y-axis here is going to be your next step. Yeah. And you're going to have a different matrix for the action of opening or pulling, and you're going to have a different matrix for the action of closing or leaving. Or sorry, yeah, the actions are pull and leave. So you'll have one matrix for pull and one more matrix for leave. Right? Okay. So what this is going to look like practically is the matrix for when you do pulling is going to look like this, and matrix for when you do leaving is going to look like this. And let's unpack why that makes sense, right? So what this matrix is saying is that if you were closed and you executed pulling, the likelihood of being open is 0.7, the likelihood of being closed is 0.3, right? And if you were open and you executed pulling, the likelihood of being open is 0.8, and the likelihood of being closed is 0.2, right, at the next step. Right, so you can think of these are the previous outcomes, these are the next outcomes, O and C. And so this makes sense because if you're open, it's higher likelihood that you will be open if you executed pull, because the door's already open. Right? So it kind of intuitively makes sense that like this thing is higher than this thing, right? It's like if it is open, it's more likely to remain open if I did the pull. But there's some likelihood that it'll get closed because in the process of pulling an already open door, you might close it, right? And so that's why it's not 1 and 0. Okay, so remember that the columns add to 1, but the rows don't have to add to 1. Yeah. Does it make sense? Intuitively, does it make sense? Questions? Okay. And the leaving is intuitive too. It's saying that if you were already closed and you like didn't touch the door, it's not going to like magically open, right? So it might, but not in this model. So it's like if you're already closed, the likelihood you're going to be open is and you didn't touch the door, the likelihood you're going to be open is 0. Likelihood you're going to be closed is 1. So it's saying that if you're closed, you didn't do anything, the system's going to be closed. And then what it's saying is that if you're already open, there's a 50% likelihood that the door closes and a 50% likelihood that the door remains open. And the idea is that there might be some gust of wind that closes your door, or something else might happen in your environment that like closes your door by chance if it's open, right? And so that's the model we're going to go with. Remember, there's a model. We made up these likelihoods. But we're going to talk about how to make this like mirror reality more. But this is just a system I made up. Yes.
Also, when you close the door,
When you close the door, so the two actions are pulling and then leaving. So there's no action of closing.
but when you leave the door, what if a gust of wind opens it? So this will probably like.
Yeah, so I guess in this model right now, it's saying that if the door is closed, just because the door is heavy and it's like harder to, let's say it has a latch or something, it's harder to open a closed door, and it's easier to close an open door. But you could have a model, for instance, that has that feature. You could. Okay, so that's the system we're going to be thinking about, right? And then we also want to think about the measurement model. So this is just the motion model. It just says, this is where you were. These are the states of the world. So remember, these are states. You actually don't know if the door is open or closed. You will just receive a measurement. You like throw a sensor and you'll have a door open sensor. It'll tell you whether the thing is open or closed, but it's not a fully accurate sensor. And so you don't actually know if the door is open or closed. What you have is a measurement model. And you have like a door open sensor that either gives you open or gives you closed. Yeah. And so this is going to be your P of ZT given XT. And it's going to say that if your door was open, it's going to return open with 0.6 likelihood. And if your door was closed, it's going to return open with 0.2 likelihood, right? So what it's saying is that like what these matrices are showing is basically this. It's P of ZT given that the door is actually open versus ZT given that the door is actually closed. Right? So the sensors are clearly noisy because it's saying that, if the sensors were not noisy, this would be 1, 0, 0, 1. That would be like a perfect sensor, right? But we're saying that the door sensor is noisy because if it's open, it doesn't always return open. It's going to return open with 60% likelihood. It's going to say 0.6. And if it is actually closed, it's going to return open with 20%. Right? And so this one and this vector is saying that if the door was actually open, you'll get likelihood of 0.4 that it reports closed. And if the door was actually closed, you're going to get a likelihood of 0.8 that it reports closed. Right? So here you're going to have like these things sum to 1, but these things don't have to sum to 1. Right? So like whenever you look, if you go and look back at these slides, this is basically the key to read these guys. Right? The thing on the left is the key to read the things on the right. And so it's saying that the sensors are noisy. So if the system was actually open, it only says that it was open with 60%. And if the system was actually closed, it only says it's closed with 80%. Right? So that's the model of our sensor we're going to use. Okay, does it make sense? We're going to just run through the exercise of doing Bayesian filtering, but your model in reality is going to look different. It's just a noisy model. Okay, so given this system, let's start by saying that our belief at the first time step is that we believe that the door was open with 40% likelihood and closed with 60% likelihood. Right? So 0.4 open, 0.6 closed. Yes? Okay, so the first step we're going to do is we're going to execute the action of pulling, right? So the system has executed the action of pulling, and now we want to find out the belief bar at the next time step when you take the action, but you haven't taken the next measurement, right? And so what we're going to try and do is we're going to try and work out what belief bar is. Remember, belief at x0 was 0.4, 0.6, right? We are going to try and work out what is belief bar when you incorporate the action, but not the next measurement. Okay. And so you can kind of like implement this summation through just a matrix multiplication. And so what you'll get is belief bar is equal to that matrix we had of transitions from earlier multiplied by your previous belief. And so you can kind of see how matrix multiply works. You can see the top, like when you actually do the mechanics of matrix multiply, this is going to give you the first row is going to be sum p of xt equal to O, xt minus 1 equal to O, given ut times p of xt minus 1 equal to O, plus p of xt equal to O, given xt minus 1 equal to c ut times p of xt minus 1 equal to c, right? Just multiply the row and the column, right? And that's kind of exactly the same as this guy. Right? Like look at it, it's like you took the motion model, you multiplied by the previous belief. You took the motion model, you multiplied by the previous belief. Right? So the process of implementing that motion model step is just the same as matrix multiply. Okay, so let's do this matrix multiply. And so we know the action we took was pulling, right? So we're only going to be concerned with the transition dynamics for pulling. And so we're going to have this matrix that we multiply with 0.4, 0.6, right? So the likelihood that the door is open is now going to be, 0.8 times 0.4 plus 0.7 times 0.6, right? Which is going to be 0.32 plus 0.42, which is going to be 0.7. Yeah. So all we got, like, you can kind of think of this as like, let's intuit it. You're like 40% chance of being open, right? And you're saying that if you are open, you have an 80% chance that after pulling it was open. So the likelihood that it is open is going to be this times this plus 0.6, which is the likelihood of it being closed, times 0.7, which is the likelihood of it going from close to open when you do pulling, right? So it's going to be 0.32 plus 0.42, which is 0.74. Right? And similarly, you can do the same thing here, which is going to be 0.2 times 0.4 plus 0.3 times 0.6, which is 0.08 plus 0.18, which is 0.26. Right? And so let's make sure that this passes a sanity check, right? Your previous likelihood was 40% open, 60% closed, but you executed the pulling action. The pulling action is a higher likelihood of opening the door than of leaving the door closed. And so your belief bar over whether the door was open increased, right? So it increased to like 75% open. And so intuitively, this makes sense. Once you executed pulling, your likelihood of the door being open is 75%-ish, 74%. Yeah.
That grid matrix where every single possible action is.
So your dynamics model is essentially P of xt given xt minus 1 ut, right? So it's going to be like, let's say there were k of these and k of these and m of these. It's going to be a table of k times m. Right, so you can kind of think of it as a 3D matrix or 3D whatever tensor. Yep. Okay, so this kind of passed our sanity check. We had 40, 60 after pulling. It's going to be 74% open, 26% closed. Make sense? Okay, so now we are going to take a measurement, and our measurement is going to say that the sensor is going to say closed, right? So our belief is that it's 74% open, but we took a measurement, our measurement said closed. Actually, before we get to here, question is, why didn't it go to 100% open and 0% closed? Like if I pull a door open, shouldn't it just be open? Like why didn't it go straight to 100%?
I guess our model has stated that if you pull an open door or closed door, it's not necessarily gonna.
That's right. That's right. So there's always uncertainty. There's uncertainty in your model. So even if you pull it, it doesn't always go to open. Right? And so, okay. So we took a measurement. The measurement said closed. Now we're going to try and work through how to go from belief bar to belief, right? So belief bar didn't incorporate the measurement. Belief does, right? So what we're going to try and get now is we're going to get to belief, which is going to be take your belief bar, which in our case was 0.74 and 0.26, multiply it by the likelihood under the measurement model, and then normalize it, right? So in our case, our belief bar we knew is this. Our measurement model, I forget exactly what it was, but it's going to be the likelihood that you got so the measurement you got was closed, right? And so there's going to be the likelihood that you got closed if the door was actually open, and there's going to be the likelihood that you got closed if the door was actually closed, right? And then you're going to normalize that to be something that sums to 1. Okay, so what we are going to do is kind of just look up our table. Our table says that if my door was actually open, the likelihood I got closed was 0.4. And if my door was closed, the likelihood that I got it closed as my sensor rating was 0.8. That's the sensor model we had back here, right? So it says that the likelihood of getting closed is 0.4 if you're open and 0.8 if you're closed. Yeah. So that's just what we had defined earlier. And so we're now going to take our previous model, our previous likelihoods, which was 0.74, 0.26, multiply them by 0.4, 0.8, right? And so now you're going to get 0.296, 0.208, and you're just going to normalize it so it's a proper probability distribution. And so it'll come out to 0.58, 0.42. Let's not worry about the math there. It's just like arithmetic. But the point is that let's kind of intuit what happened. It's like I had a 74% likelihood that the door was open, but then I got a closed measurement, right? And so the closed measurement is going to help me correct my belief. And so the likelihood I got a closed measurement if the door is actually open is 0.4, and the likelihood that I got a closed measurement if the door is closed is 0.8, right? And so it's going to bring me closer to the belief that the door is closed, right? So I like increase my likelihood that the door was open through my action, and then the measurement kind of reduced my belief that the door was open, right? And so now you can see that we went from our previous belief, which was 0.74, 0.26 to 0.58, 0.42. So you brought it back down. Yes. Eta is the sum of the entries. So eta is basically 0.296 plus 0.208. Or it's like 1 over that. And so that's going to help you normalize. It's harder to do this when you're not in a table. In a table, it's always easy to normalize the row or column, but it's harder to do that in like a continuous. Okay, does this parse overall? Does it make sense? Let's kind of like think about this. How do we go about this? We thought the door was open with 40% likelihood. We took an action. The door is now open with 75% likelihood. We got a closed measurement, and so it brought it down to 58% likelihood. And this will keep repeating, right? And so what this kind of suggests is that there are certain actions that are information gathering, like certain things will give you more information than others. And so in these kinds of systems, you can also, right now we're assuming the actions are given by someone, but there's an interesting line of work on how to gather information more effectively to figure out where you are. Like for instance, if I want to localize myself, I can drive into the wall and I kind of know where I am, right? Don't do that, but generally. Okay, let's go through one more quick intuitive example. This is from Dieter's textbook, which is excellent. You all should read it. But it's basically you have a robot. It has a uniform likelihood of where it is. It's at these it's in this hallway where there's 3 doors, right? And it's trying to figure out where it is. It has a uniform likelihood. Then the first thing it does is take a no-op action. So when you take a no-op action, you just don't move, right? So if you take a no-op action, you don't move, your belief doesn't change, your belief remains exactly the same. Then what you're going to do is you're going to take an action where you're going to get a measurement, and the measurement returns door, right? So the measurement is either door or no door. And so it says like you basically knock on the wall, and if it's hollow, it's door. If it's not hollow, it's no door, right? And so the measurement you got was door, which means that like it's either here, here, or here, right? So you can see the belief now, which was uniform, has now gone to like peaking at these 3 positions. You don't know which of the doors you're at. You just know you're at a door, right? And so the first thing you did was you didn't move, measurement, belief didn't change. Then you took a door measurement and you're like, I'm at a door. I don't know where I'm at. I'm either here, here, or here. Yes? Now, the next thing you're going to do is you're going to take an action of moving 3 meters to the right. Okay? So intuitively, what you'll see is that your belief, which was previously here, right, has now moved 3 meters to the right. And so like if you look at this thing, this is like kind of like a shifted version of the previous thing. But you can also see that the peaks are less sharp because you added more uncertainty, right? Because there's some uncertainty. So you kind of moved everything over to the right. That's kind of your prediction step. You move things over. Now you're going to take another measurement, and your other measurement also says door, right? So your measurement model is going to upweight, if your measurement model is going to be non-zero if it's here, here, or here, right? Those are the 3 doors. And what that's going to do to your belief is it's going to say, hey, like, given your previous belief, which was there, right? You try to see if you like weight this thing by the measurement model, like the only one that actually overlaps is this guy. And so it's going to like spike up, right? So it's going to say that your belief is now going to be really high around here. So you kind of know that your robot is here, right? So what that's kind of let you do is localize where you are just through this process of motion measurement, motion measurement, motion measurement. Yeah. Okay, so now we're ready for world domination. But one question to ask is, do actions always increase uncertainty? Like if I take an action, will it always increase uncertainty, or does it not always do that? So we talked about driving into the wall as one example. What's another example that could reduce uncertainty?
Yes, if you, I mean, it's data there, but if you do the same thing over and over again, you get, I guess, consistent measurements. That should lower your uncertainty.
Yeah, so
if it's like an actuator like this, if you're at the end of the range of motion.
exactly. Yeah. So I think so this example is from Sid's group. But basically what they're trying to do is they're trying to like gauge a system and use like gauging to kind of know where you're going to be. So it says that like certain actions will kind of reduce uncertainty because it like forces it into a funnel where it's like you know where it's going to be. And so kind of like funnels things to be low uncertainty. So like as a rule of thumb in your car, for instance, most things will increase uncertainty, but there are certain examples where that doesn't happen. So don't like take that as a rule of thumb. The converse question is, do measurements always reduce uncertainty?